Hello, everybody, and welcome to Lecture 8, the second part of Lecture 8, where we will continue our study of root systems. This is the second last lecture, and in the next lecture, we're going to go back to Lie algebras and show how root systems can be used to classify semi-simple Lie algebras. But for this lecture, we're going to continue solely with root systems, and no explicit mention of Lie algebras will be made. Okay, so let's recall quickly what a root system was. So we were just starting with a real vector space, E, endowed with an inner product. So before we were dealing with general symmetric bilinear forms, here we're dealing with a very special case of an inner product where everything is symmetric, bilinear, positive, definite map. So, and we'll call the real vector space endowed with this inner product, this finite dimensional inner product space, we'll usually refer to it as Euclidean space. That's what the E stands for. So a root system is going to be a finite subset of our Euclidean space, not containing zero. We call the elements roots, and we have a system of conditions on these roots. So we want that this root system spans the vector space. We want that whenever we take a root, alpha inside and delta, the only way that we can multiply it by a scalar and still get a root, still get something that's inside an alpha, is if the scalar was plus or minus 1. Anything else would land us outside of the root system. Okay. So we can see from the start here that this means that delta is definitely not a linearly independent set, because if you have any alpha in there, minus alpha is also in there, so the set can't be linearly independent. So it's certainly not a basis or anything like this. Moreover, you see that it's, well, of course, it can't be a subspace because it's finite. So any subspace is going to have an infinite number of elements inside there, whereas this has a finite number of elements. But you see that there's very little real number structure on this. It's really more of an integral thing. So moving on to the third condition, and this is the key condition, I guess. This really is the key condition. You're asking that this root system, this finite set of subsets inside a Euclidean space has got a very special type of symmetry. And the symmetry is given by reflections, what we call reflections in the roots. So so this here is the quantity that we're taking. So how you should look at this is, if we were to take our root alpha, now using a Gram-Schmidt process, then we can always extend this single element, the single vector inside a Euclidean space up to an orthonormal basis. Now, in that case, for our lambda in E, the coefficient of lambda, the alpha coefficient of lambda with respect, sorry, there's an alpha missing here. The alpha coefficient of lambda with respect to this orthonormal basis is going to be precisely this. Okay, so this is the projection of lambda onto the unit vector alpha, sorry, onto the vector alpha, and then we've normalized it so that it's a unit vector. Okay. So again, as I said, an orthonormal basis. So first of all, in order to get an orthonormal basis, we have to normalize alpha itself and then extend it up to an orthonormal basis. This is like the normalization of alpha. And then we've got the projection of lambda onto alpha. Okay, and then what we're doing is we're going to subtract this. So this is just going to give you this it's going to subtract the coefficient of alpha with respect to this orthonormal basis, and hence give you a reflection just in the alpha. Okay, and basically in all of the other directions, it will just be the identity. And then we want that with respect to this reflection, with respect to this definition of reflection, the reflection of alpha will map your root system into your root system for all alpha. So you somehow use an element of the root system to construct a reflection, and then you have to have that the root system itself will be preserved from this reflection. And then finally, we want to impose an extra condition on this element here, this scalar. We want that this is actually an integer. Okay. And that's somehow at the heart of root systems, is that you have this symmetry involved there, and you also have that the symmetry is somehow integer in notion. People talking about it being crystallographic because it starts to look like a lattice. But you want, you want that the symmetry, the defining symmetry of the root system, to have at its heart this integer structure, which is to say you ask that the coefficient involved in defining the reflection is actually an integer. Okay. You can in fact remove this condition here if you want, and then you get something which is called, you get a generalized root system, and more specifically this is called a reduced root system, but we won't worry about such things here. So let's clear all that away. Okay, so now, as we just saw, the elements of the root system do not form a linearly independent set. And we'd like to now study root systems by finding a very natural subset that gets rid of these linear dependencies somehow. We want to pick something smaller inside there that has linear independence. We call this thing a base because, first of all, it's asked to be linearly independent, which is to say a basis of E. So we're picking a subset, and we want that subset to still span the whole space, but we want the fact that we have fewer elements to mean that it's linearly independent. Okay, so we want that capital Pi as a basis. Now, we also want the way that it spans the space to interact with the root system itself. And this is where the integers come back into it again. You'll see integers appearing just like at the end of the previous definition. So we want that for any root beta, any element inside in our delta, that we can express it as a linear combination of integers, so that somehow the roots are given by integer linear coefficients of the whole space, of the base. But we impose an extra condition that basically we can only do it in one of two ways. Option one is when all of the integer coefficients are greater than or equal to 0. Or option two is when all of the integer coefficients are less than or equal to 0. You're not allowed to mix them up. So this is somehow, the base is imposing like this decomposition of your root vectors into two parts, into like these ones which are positive linear combinations and ones which are negative linear combinations. So quite reasonably strong. So the question, of course, is when you look at something like this, do such things exist? Is it too strong and then only some root systems will admit a base? Or is it just right and every root system admits a base? Well, you'll have to wait and see. And we call such elements, we call elements of a base, refer to them as simple roots. Okay, so just to recap, a base is going to be a basis. It's a subset of a root system, which is a basis, which spans the space and is linearly independent, and also spans the root space in this integer coefficient way, positive or negative. Now, with simple here, in the next slide, we're going to justify why we call these things simple roots. Sorry, no, in the slide afterwards. So here, just there's an observation to make, first of all. Positive root system, as I was saying, if you have the existence of a root system, then basically immediately you get the notion of a positive root system or a negative root system. You get a definition of positive or negative roots. The positive roots are the ones that are going to be positive integer linear coefficients of your base. And the negative ones are going to be the ones which are negative integer linear combinations of the elements of your base. Or equivalently, you can just put a minus here. Okay. because you can see this, because everything is either in the positive span or the negative span. If it's in the positive span, then minus it will be contained in the, remember that if we have a root inside in our root system, if we apply minus, then we still get an element inside in the root system. It's closed under multiplication by -1. But then clearly this thing would be contained inside of the negative linear span, and vice versa. So you can see that these two things are equivalent. Okay, but what's most important is that this breaks it up. Okay, we get a decomposition of a root system into positive or negative. But this is a choice. It's a choice coming from our choice of root system. Right? So now we can go on and justify this notion of simplicity that we had before. So let gamma be a base, and let pi be a base, and let alpha be an element of pi. Then it is not possible to write alpha as a sum of an alpha prime and an alpha double prime, where alpha prime and alpha double prime are two non-zero elements of the positive roots. Positive roots with respect to our choice of base system, or with respect to our choice of base capital Pi. Okay, that's somehow where the word simple comes from. It's not possible to break them up into the sum of two non-zero elements. Think back to Lie algebra being simple when we couldn't break it up into a sum. Being simple when you couldn't break it up into a sum of two ideals. Moreover, what we know is that whenever alpha and beta are two distinct elements of pi, two distinct simple roots, then we have that the inner product of alpha and beta is less than or equal to 0. That will come as a consequence of the fact that they're simple, that we can't break them up into the sum of alpha prime and alpha double prime. So how do we show that they're simple? Well, let's assume that we have a decomposition of alpha into alpha prime plus alpha double prime for two non-zero alpha prime, alpha double prime. And let us expand each of these elements in terms of the base capital Pi. Okay, so we denote alpha prime. It's just going to be, what we're denoting here is just the coefficients, eta prime and eta double prime. These are elements of the base. We can expand them out because remember that one of the conditions of the base was that any other root could be obtained as a positive, any positive root could be obtained as a positive integer coefficient. Positive integer coefficient linear combination of the elements of the base. Okay. Now, since the elements of gamma are linearly independent, they're a basis of the space, that must mean that when we add up alpha prime and alpha double prime, all we're going to be doing is adding up the coefficients eta prime and eta double prime. But these have to match. So the expansion of alpha in terms of the basis is simply alpha, because all of the other coefficients are going to be 0. So then that means that the coefficient on beta, this eta prime beta plus eta double prime beta, this is going to have to be 0. Because we have no contribution of beta in this sum. This is the decomposition into a direct sum of elements in terms of the base, because alpha is a base element for beta not equal to alpha. And when it is, then the coefficient here for alpha is just going to be 1. So that means that eta prime alpha and eta double prime alpha, they're going to have to add up to 1. But because these are positive roots, these coefficients here are all greater than or equal to 0. Now, the only way that two integers which are greater than or equal to 0 can add up to 0 is if they're both 0. And over here, the only way that two non-negative integers can add up to 1 is if one of them is 1 and the other is 0. If the first coefficient, if alpha eta prime is equal to 0, then that means, because all the other coefficients inside an alpha prime are 0, if this in addition is 0, then that means alpha prime is 0. And similarly, if eta double prime is equal to 0, then alpha double prime is 0. But that's a contradiction because we assumed that our alpha and alpha prime were both non-zero, because that's what we're trying to prove. Thus, we see that any two elements of a base cannot be broken apart into a sum of two non-zero positive roots. Okay. So now let's use that to prove the second statement, that whenever we take an inner product of two distinct roots, we're going to get something which is less than or equal to 0. Not strictly less than or equal to, because it can happen that two roots, when you take their inner product, two distinct roots, when you take their inner product, then it's going to be less than 0. Note, of course, that if they're not distinct, if it's alpha and alpha, then of course this has to be greater than 0 because it's an inner product, and an inner product by definition is going to be positive definite, which means precisely that the inner product of alpha and alpha is greater than 0, strictly greater than 0. No, so as before, let's just assume that the opposite holds, and let's draw a contradiction. So if alpha and beta are greater than 0, if the inner product of alpha and beta is greater than 0, then from our previous lecture, remember that for roots, you can't take sums of roots and expect to land back inside your root system. It's not closed under addition. It's not closed under taking differences. It's quite sensitive like this to how you can add roots together. Remember that when we want to multiply by a scalar, the only scalar that we can multiply to remain inside in our root system is by plus or minus 1. And as we saw, to have sums or differences inside there, this condition is sufficient. Okay, in general, they're not, but if the inner product is greater than 0, then the difference is contained inside your root system. Okay, this is what we proved in the last lecture. So if we assume that this is true, then if we assume that this is true, then we're going to get this. We're going to get the difference of these two things is contained in the root system. So let's denote that new root by beta prime. Now, we have two options. Remember that when we make a choice of basis, we decompose our roots into two subsets, the positive and the negative. So either beta prime has to be contained either in the positive, either in the negative. There's no other choice. So let's assume that it lives inside in the positive roots. Then we would have that alpha was equal to, so if it's here, we can just bring this across to the other side, and we're going to end up with beta plus beta prime. This is positive by assumption. Okay, and now this is positive by assumption. Now we've shown that this is positive. So, but that would then mean that alpha was not simple because we've decomposed it into a direct sum of two positive roots. Okay, but if on the other hand, beta prime were in the negative roots, then beta, we've brought beta over here and we've brought this beta across and it becomes minus beta prime. But now, because beta prime is a negative root, minus beta prime is a positive root. So now we've decomposed beta into the sum of two positive roots. So again, we see that beta is not simple, but that also contradicts our assumption starting off that alpha and beta were both simple. So to avoid contradiction, we have to assume that the inner product of two simple roots is always less than or equal to 0. Okay, so now the natural question to ask is, do bases exist? Because if they don't exist for every vector, for every root system, then it's a less useful notion. If they do, then it highlights the sort of positive negative structure of a root system and could serve to be a very good way of looking at these things. So as the title here suggests, in fact, it is possible. One can always construct a base for a root system. But it's not obvious, and we need to put some work into actually proving that this is the case. Okay, so how are we going to do it? Well, we're going to introduce, so recall we had in the last lecture, we spoke about the hyperplane associated to a simple root. So we're going to take all of those lambdas inside in our Euclidean space, all elements of the Euclidean space, such that the inner product with lambda is going to be 0. They're all the elements that are orthogonal to alpha. Okay, you can see that this forms a vector space. vector subspace. Now we call, if we take the union of all of these hyperplanes, so it's a finite union because a root system is a finite collection of elements, finite collection of vectors, then we call any element that's in the complement, we remove the union of all of these hyperplanes from E. And any element that's in there is called a regular vector. Now, such vectors exist because an inner product cannot be covered by a finite collection of hyperplanes. So this is a well-known result. The proof is reasonably elementary. We won't go through it here. But for those of you who want to see the proof, think about it yourself and try to prove it yourself, and you'll probably get it. It's usually left as an exercise. If not, send me an email and I can, or in the later version of the notes, I'll give you a reference. But here we're just going to accept it. So such vectors always exist. And now what we do is we form an analog of the positive and negative roots using this vector. Okay, so we just put delta plus of gamma is going to be equal to all of those elements inside in the root system, all of those roots. And sorry, that should be an alpha. That should be an alpha, because we'll always denote elements of a root space with Greek letters. Now, the set delta plus is going to be composed of all of those such that when you take the inner product with gamma, the result is greater than 0. And when you take the minus is going to go whenever you take the inner product with gamma, you're going to get something less than 0. Now that divides up the whole set because it's a real inner product. So the only options we have out of any inner product are that it's going to be something strictly less than 0, strictly greater than 0, or 0. But it can't be 0. Okay, because gamma is outside, it's not in the orthogonal complement to any root. So it doesn't pair, it has a non-zero pairing with every root. Hence, we've only got the options of strictly greater than 0, strictly greater than 0. And that's what we use to break up the root system into two subsets. So now we denote by pi of gamma. We're now going to construct something like simple roots with respect to this gamma. I guess as you can see here, when we go back, what we're going to do is use gamma to construct a base, for a root system. And when we do, these will be the positive and negative roots associated to this base. Now, we denote by pi of gamma the roots contained in delta plus of gamma that cannot be written as a sum of two positive roots. Okay. So if this was a base, then this would be a property. But we're sort of going the other way around because we're trying to construct the base. And the way we're going to do it is we're guessing that if we look at those positive roots, remember, of course, that your base was always, more or less by definition, always contained inside in the positive roots. So we're going to guess that by decomposing our root subsystem into positives and negatives, and then looking at the simple elements inside in the positive part, that these will actually give us a basis. That's the guess. Okay, so let's try to make that guess work. First, we see that for any positive root, we claim that we can write this positive root as a positive integer linear coefficient combination of elements in our base. Okay, and similarly for any of the negative, that they can be written as positive. That's a typo. It should be less than or equal to 0, of course. Okay, so this is important because for pi of gamma to be a basis, it needs to span the root systems in this positive and negative integer coefficient manner, and it needs to be a basis for the whole space. So if we prove this lemma, we're halfway there. Okay, so let's see if we can do that. Okay, so let beta positive, well, a gamma positive root, let this be a root which is not expressible in the claimed form. So there's not some linear combination of the elements of pi of gamma that's equal to beta. Okay. Again, what we're doing is we're assuming that the thing we don't want to exist exists, and then we're going to try to derive a contradiction. Now, since delta, a root system, is finite, there will in particular, there can of course only be a finite number of such elements. So this beta is some special type of root. There are only a finite number of type of roots. There are only a finite number of roots, so there can only be a finite number of special type of roots, obviously. That means then that if we look at this quantity, if we look at all such beta, if we look at the finite set of all such beta, and then we look at this scalar, this real number, there will be a finite number of these. Okay, they have to be positive, remember, because beta is a positive root. Remember, we used gamma to break our roots into positive and negative, and this is precisely the defining condition of being a positive root, is that gamma beta is greater than or equal to 0. But we want to choose this to be as small as possible. So, you know, in general, if you have some sort of infinite set of real numbers, choosing something as small as possible is not possible. But we've got a finite set, so everything is fine. Now, beta cannot be contained inside in gamma pi. Why not? Because if it were, then it would be expressible as a linear combination of elements pi, namely just itself multiplied by 1. So it's definitely not in gamma pi. But if it's not in gamma pi, that means that it's in gamma pi if it's not expressible as a sum of two non-zero positive elements. Hence, if it's not in gamma pi, that means it is expressible in terms of these two elements. So it has to be. So let's denote these elements by beta prime and beta double prime. So beta is going to be equal to beta plus beta double prime, where beta and beta double prime are non-zero. Now, by linearity, if I now take this element and I pair it with gamma, I know, of course, that this thing has to be greater than or equal to 0. And now, because these are positive, and because beta prime and beta double prime are positive, these things are also greater than or equal to 0. Okay. So it's the sum of two strictly positive real numbers. But now, I'm giving us, of course, this strict inequality here. Because both of these are that should no. It's definitely not. That's the whole point. Remember, that's why we chose gamma to be a regular vector, to be contained in the difference of E in the hyperplanes, is because it always paired with every root to give you a strictly non-zero. So sorry, it should not be inequality. Same here. It's going to be the sum of two strictly positive real numbers, these two guys here. And of course, that means that they'll have to be strictly less than. Okay. We can only have an equality here if one of these was 0, but it's definitely not 0. So it's going to be strictly less than. But no, at least one of the beta prime and beta double prime cannot be expressed as a positive linear combination of the elements of gamma prime. Okay, because if they were, then that would give us an expression of beta in terms of the basis, positive integer coefficient expression of beta. So that would violate the original assumption here. So then we have to conclude that at least one of these that at least one of these isn't, but then that means that contradicts our assumption that gamma beta is as small as possible. Okay, so basically to avoid contradiction, we'll have to conclude that no such beta can exist. Which means in particular that, let's go back up just to see what we've proved. Here we are. Basically, we've now shown this. We've shown that every positive root can be expressed as a linear combination of this one. Okay. For the case of a negative root beta, we can consider minus beta, which lives inside in positive roots. We can expand it now in terms of these proposed simple roots. I mean, here our simple roots are really all right, our simple roots, what do we mean by this here? Remember, this is just pi. It's the simple roots with respect to gamma. All right. Expand it, and then we multiply by -1 to go back, get back to beta, and now we have a linear combination of the required form. And that's it, we're done. So we've now basically shown that by taking this regular vector gamma, producing these positive and negative roots, then defining the simple roots in the positive part to be those ones that can't be expressed as a direct sum of two other positive roots. We've now produced something that satisfies half the requirements of a base. Okay. So let's go on and finish the job. And what's left? To prove that this set of positive elements defined in terms of a regular vector gamma, what's left to prove that this is a base? What's left is just that it's a basis of the whole space. So a basis does two things. One, it spans it, but that's easy because that's what we observe here. We've seen that any positive root is a linear combination of the elements of gamma, and any negative root is a linear combination of, well, actually, sir, we don't need positive here. I should just get rid of that. That any positive root is a linear combination of the positive elements, of the elements of pi of gamma. But the roots span the whole space. So if you've got a space that spans a spanning set, then it spans the whole space. So all we need to do is prove is to prove that it's a linearly independent set. Okay. Now, using the same arguments as for simple roots that are defined in terms of a general basis, not the ones defined in terms of pi of gamma, we can also show that alpha beta is less than 0 for two distinct alpha and beta contained inside capital pi of gamma. Okay. Exactly the same argument. Go back and look at it and see that any of the assumptions that we use to prove this hold for this pi of gamma, just as they did for pi. So let's use this to show that the elements of pi of gamma are linearly independent. So let's assume that we have, that's as we're used to, let's assume that we've got linearly dependent set. Okay, let's assume. Now again, look, this is linear dependence for the real numbers, okay? Because it wants to be a basis of the real vector space. So when we're dealing with the interaction between the base and the root system, then everything is integers. When we're dealing with the interaction between the base and the entire, it's going to have to be real integers because it needs to be a real vector space basis. So let's assume that such a linear combination exists and gives us 0. So let's collect together the terms with positive coefficients And let's collect together the terms with negative coefficients. And then we're just going to bring the ones with negative coefficients to the other side. Okay, just going to break it up into positive and negative, and then we bring the negative one. Then we bring the negative ones over to here, and we get precisely this, okay? And the two of these, of course, will have to be equal. And now we're going to denote this new element by x. Hence, we see that when we take the inner product of x and x, then we're going to get nu sub alpha by minus nu sub beta by alpha, the inner product of alpha and beta, where the summation here is going over all alpha and beta, depending on whether the coefficient is positive or negative. Okay. But now what we just saw above, what we remarked above, was that the inner product of these two simple roots in the sense of simple with respect to the choice of a regular vector gamma, this is going to be less than 0, this quantity here, okay? Less than or equal to 0. But this is positive, because it's up here. Now, this is negative, but minus this is positive. So we have positive by negative. So that means that this thing is going to have to be less than negative or 0. It means that this whole thing then is going to have to be less than or equal to 0. So we've now got the inner product of an element with itself, and its value is less than or equal to 0. But of course, for an inner product, you've got positive definiteness. So the inner product of x and x is always going to be strictly greater than 0 whenever x is non-zero. Hence, we have to conclude that x is 0. So it means that both of these sums here are equal to 0. Now, since x is equal to 0, clearly we're going to have this. I mean, an inner product is a bilinear map, so of course if we pair with anything that's a 0, it's going to be 0. Now, expanding out what x was in terms of this linear combination, so it was a linear combination where we summed over the strictly positive coefficients. Of course, in this expansion of this linear combination, this linearly dependent combination, we're going to assume without loss of generality that all of the coefficients are greater than or non-zero, either greater than or less than. Because obviously otherwise it would be trivial. We can remove anything which is 0. Now taking that and putting it into this expression, we get this. But now, okay, if we look back to what we had done before, you see that, this of course should be gamma, and it should be the other way around. So since alpha gamma is greater than 0, we show that because the two of these things, because of the definition. So alpha is contained inside the positive roots. The positive roots of gamma, should be more precise here. It's contained inside the positive roots of gamma. And the definition, by definition, you're inside there if this pairing here, this inner product here is going to be greater than 0. Positivity refers to. Okay. So that then, together with the fact that these here are assumed to be real numbers strictly greater than 0, implies a contradiction. You can't have a sum of real numbers which are all strictly greater than 0 adding up to 0. So we have a contradiction. So we have to conclude that no such linear combination actually exists, which means that our elements are linearly independent. And since we already knew that it was spanning set, that means that it's a basis. And then when that is taken together with the previous lemma, where we showed that every element of the root space could be expressed as a positive or negative integer linear combination, that means we've satisfied the conditions for pi of gamma to be a basis, to be a base of a root system. And that's great. So that means in particular that every root system admits a base, which means that it's a good idea, which means that it's something that is going to be a useful tool when trying to study root systems. Now, and in particular means that we can always make this choice of a basis, which then gives us this decomposition of positive and negative roots. So this positive and negative is a central part of the definition of a root system, which I guess you can think of as coming from the condition, the initial axiom in a root system, that whenever I multiply by -1, I've always got another root in there. So somehow this choice of a base, you can also think about as making a choice of which one is positive or negative. I mean, of course, if you've got alpha and then you look at minus alpha, it's not clear which one of them to call negative, because of course you can look at alpha as minus alpha. So you somehow need to make a choice of which vectors are positive and which vectors are negative in these pairs, these plus minus pairs that we have. And that can actually be shown to be equivalent to the choice of a basis. It's another way of coming at the definition of a base. We won't recall it here, you already have enough information. But just remember that think about this. You can think about the condition of a base sort of coming from, or at least the existence of the positive and negative roots coming from base as coming from this last axiom or second axiom that we gave in the definition of the root system. What we can also show is that any base can actually be constructed from a root system in this way. We won't have time to go into the proof and we don't need it later on, but just remember that this construction to this regular vector gamma can actually realize every base, which is to say, whenever you see a base, there will be an associated regular vector gamma, but that won't be unique. A good way to explore or to get some feeling for this regular vector stuff is when you look at the root systems of rank 2. And when you draw, I mean, one of these regular vectors is just going to be a line in the plane going through 0 that is not perpendicular to any element of the root system. That's easy enough to do. And then you're going to define your positive or negative depending on how they project onto, if they're pointing in the negative direction of the vector or pointing in the positive direction of the vector. Of course, you need to choose a positive or a negative. But anyway, let's move on. So let's go back to our root system A to the n, the one that we've been using as a motivating example all along. So if you just recall that, what was it, the root system? Well, the Euclidean space that we were looking at, the Euclidean space lived inside an R to the n plus 1. So it was an n, and it was a one-dimensional space. So we're imposing one relation here, that all of the elements add up to 1. So in fact, it's going to be n-dimensional. And then we show a root system, the root system that we were going to look at. Again, for any rank, there can be many root systems, but the root system that we're going to look at was this. It was just going to be the difference of our two basis vectors, the canonical basis vectors for R to the n plus 1. Okay, just the difference of the two of these. So now what we're going to do is we're going to choose a subset of this, which is to say we're going to choose a base. And what do we do? Well, we choose these roots. So it's going to be alpha I plus 1. Okay, so we're just basically asking that we're looking at I, that when we have the I and the j, it's going to be I, and then the one that we're subtracting is going to be I plus 1. Which is to say, that's a bad one, but hopefully you can see, okay. Which is basically just saying that j is going to be always equal to I plus 1. Okay. So now we have to show that this is a basis. How do we show it? Well, For it to be a base, it has in particular to be a basis. But we see that these vectors, these alpha sub i's, they're clearly linearly independent. Okay. They're clearly linearly independent. And there are n of them. So that means they have to be a basis. Okay, because E is n dimensional. What's going to maybe less immediate, but not difficult, is showing that they have this integer coefficient span that you can express any other root, which is to say, if we take an arbitrary root, these alpha ij's, how can we write these alpha ij's in terms of the alpha i's? Well, it's clear. This is how it works. You just need to, for example, if I take E1 minus E2, and then I add E2 minus E3. Okay, so this is alpha 1. This guy here is alpha 2. Well, the two of these cancel. And then I'm going to get E1 minus E3. If I just keep on doing that, then I can get any alpha ij such that I is less than j. Okay, we just need to go from I up to j minus 1. How do we get the other ones? The one where I is greater than j? Well, we can see that ij is equal to minus ij. If we put the minus in front, it just switches things around. And of course, that's just equal to minus alpha sub k's. That's so it works. It's easy. So you see here in this, we actually the positive and the negative linear, the coefficients all along are just going to be basically plus or minus 1. These are our integer coefficients. And in fact, you see that basically depending on whether I is greater than j or I is less than j, it goes into the positive or the negative roots. I think, sorry, usually I was writing this as a superscript. So let's put it up there. It's just a typo. And that's it. There we see now from this that our positive roots, the one that can be expressed these positive linear coefficients, are I is less than j. So the theorem of root systems seem kind of abstract. But with these examples, you see that it's actually kind of very elementary linear algebra. I guess the hard part in the root system, and again, that wasn't so hard, is root system A to the n, was what we showed last week, that when we described completely the reflections that were coming from the simple roots, sorry, not from the simple roots, but the reflections that were coming from the roots, and we showed how they worked and showed that they observed that they permuted the root space. When then after this, the choice of bases is not so difficult. It's kind of clear. Okay. So let's move on. Now we're going to introduce the notion of a Weyl group. So this is sort of a finite group that we can associate to any root system. And it's a very important part of the structure. Okay, so a slightly new topic, but yeah, it's the third part. So I guess whenever you're looking at root systems, the first thing you look at the definition of the root system itself and consequences. Then you introduce the notion of a base for a root system, and probably the next most important thing after this is going to be the Weyl group. So what is it? It's a group generated by the reflections. So if we remember, if you took this reflection S sub alpha for any root, and we did it twice, you got back to where you were. Because you're basically just somehow you're taking a linear expansion and you're basically just changing the sign in one of the coefficients. So when you change it twice, you end up back where you started. Now we define the Weyl group of a root system to be the subgroup of the general linear group. And yeah, sorry, the point of this here is that these are linear transformations. But they're going to be they have no kernel, hence they're invertible. Okay, so they live inside of the general linear group. This is just going to be, regarding this as a vector space, and it's going to be all of the matrices which are invertible. That's what GL means here, just all of the invertible matrices operating on linear transformations on this finite dimensional vector space, which is a group, of course. So then we look at the subgroup of this group generated by the reflections, and that's the Weyl group. Just basically the group generated by the reflections. Now the Weyl group is finite, and it preserves the roots, which is to say, I mean, it's clear that the linear, by definition of the root system, the reflections preserve the root, but we're saying that the whole group, I mean, this is kind of obvious, but we're presenting it just in the lemma for sake of formality. Moreover, it is a subgroup, it's contained in the general linear group, but it's actually contained in a smaller group, the unitary group, which is to say, it satisfies this here. Whoa, okay, so there were some extra brackets here, my apologies. All right, it just means that if I apply, and yeah, the first W here has nothing to do with the second W, my apologies for that. Let's make this a bit clearer. Let's turn it into U. And of course, V and U live inside W. All right. The unitary group, and you can check that this is a group itself, is going to be all of those elements in GL of E, such that when you operate on an element of V, when you operate on V and U and you take the inner product, it doesn't change anything. That's what it means to be unitary. Or you can think about it as preserving length. Because you can think about this thing here as if I put U equal to V, then this will just be equal to this, well, actually squared, the norm. And then of course, if U is equal to V again, this is just equal to V. And of course, we can cancel the two squares. So it means that it doesn't change the norm. It doesn't change the length. Okay, that's what's going on. How do we prove this? Well, this is easy calculation. So the reflections map the root system to the root system for any alpha. Hence it's clear, because what is it? They're just going to be compositions of these reflections. So it just keeps successively applying elements that map delta into delta. Of course, continue to map delta into delta. So this is clear. This means then that we have a group homomorphism from W, from the Weyl group, to the group of permutations of W. Okay. Any element of the Weyl group is going to permute. And now this is a finite group, so the roots it's a finite set of elements. So its group of permutations is finite. Okay, so the image, at least, of W under this group homomorphism is a finite group. If we could show that this homomorphism was injective, then we'd know that W was finite. I mean, what could happen is that there was a huge kernel that killed an infinite number of things and then would turn this infinite group into something finite. But our claim is that this is not what happens. The claim is that it's actually injective. So let's imagine that we have some W in our Weyl group, some small w in big W, our Weyl group, and this was contained inside the kernel of this homomorphism. Here should be W. What does it mean for something to be? This is a kernel of a group homomorphism, a lot of linear map. So it's going to be brought to the identity element of the group, which is to say E. What is it in this case? This is a permutation group, so it's going to be the identity permutation, which is to say the thing that fixes all roots. So if something is in the kernel, then it's going to get mapped to its image under phi won't do anything. But the roots span E, okay. So since W is a linear transformation, it must be the identity map. Okay. Hence, phi has to be injective and W is finite. So finally, to show that W is contained inside the unitaries, it's enough to show it just for, I mean, if this identity here holds for the generators of the group, then we see that it's going to hold for everything. And this is just a direct calculation. It just follows basically, it's a 1-2 line calculation in terms of the definition of the 1 line calculation in terms of the definition of the reflection. And yeah, just some cancellation. I'll leave this to you as an informative exercise. So it means basically, we can think about it as that the Weyl group basically preserves, it's this finite group that's going to preserve length. So it'll preserve the length of any arrow, any vector inside it in the root system. There's another useful identity. So whenever we have a W in small w and big W, we have an alpha in the root system, then if we take the reflection given by, remember, so W is, it permutes the roots. So it's going to take any root alpha, turn it into another root alpha, but then for any root alpha, you've got an associated reflection. So we've got this new reflection. So can we express this in terms of the old reflection? Well, remember, this is also permuting the roots. And it just turns out that it's this, well, this is also an element of the Weyl group. So it's just the inverse of W, the reflection given by the original root, and finally followed by W itself again. So it's just like a conjugation. So how do we do this? Well, if we have lambda, which is contained in the hyperplane, perpendicular to alpha, then because alpha is a unitary operator, we know that this is true, and we know that this is 0, because that's the definition of H. It's going to be all of those elements such that they're perpendicular to alpha. But what does this mean? Well, this means that W alpha means that this W alpha is perpendicular, sorry, W of lambda is perpendicular to W of alpha, which means that W of lambda lives inside in W of alpha, sorry, H of W of alpha. But what this implies is that W is going to map, because again, these elements were chosen in general. So it means that W is going to map H of alpha to HW of alpha. Now, the element WS alpha inverse is going to act as the identity on WH alpha, which is equal to H of sub W alpha. And where we remember that S sub alpha is going to act as the identity on H alpha. Remember that when it does the reflection, it does nothing to the vectors which are perpendicular, and it only switches the sign of the linear span of alpha itself, but it just acts as the identity on H alpha. So in fact, this is just going to, the W inverse is going to cancel with the W inverse. The S just acts as the identity, and what are we left with? Us left with W alpha again. And it maps W alpha to minus W alpha. Okay, and then the same is true for S of W alpha. Therefore, the two things are going to be the same. This is what we saw in the last lecture. This is how S of W alpha is going to work. Okay, so there's an identity, give you a feel for how these things work, that expresses the relationship between the reflection and the general element of the Weyl group acting groups. Now, for any base pi, we call the reflection sigma sub alpha for alpha an element of pi. We call these simple reflections. Remember, these elements that were contained inside in the base were simple roots. What we do is we call the corresponding reflections, we call these simple reflections. And we don't have time to prove this here because we're coming towards the end. As usual, as always, there's never enough time. You can actually show that the simple reflections are going to generate the Weyl group. In fact, this maybe is, if you want to, you could have a go at this yourself. Or maybe even look up the proof, but it's not so difficult, but we won't have time to prove it explicitly here. And so in particular, if we go back to our example of A sub n, we now see that this is generated by the corresponding simple reflections. But what were the simple roots in this case? We're just going to be those elements alpha I, okay, just equal to alpha I and I plus 1. With the corresponding reflections, if you remember from last week, we just saw that the corresponding reflection was just going to interchange the S sub I and S sub j. So in this case, they're just going to be transpositions. They're just going to be ones that swap two elements next to each other. So then we see that these give us a generating set for the group. But of course, that means that we just got the symmetric group. It's going to be generated. Okay, I'm being a little bit careless with regards to relations here and so on, but this is basically what's going on. So the Weyl group of this A series is just going to be the symmetric group. And in fact, this is something that happens a lot, that the Weyl groups for root systems are always quite close to something like the symmetric group. But we'll see a bit more of this later on. Okay, so that's the end of this. The next day, we'll finish off root systems very quickly, then show you how semi-simple algebras give you a root system and how this allows us to classify them. And that will be the end of the course. Okay, so thank you and talk to you next time.